Good afternoon, everybody. So today I want to talk about basically three types of quantum Monte Carlo methods. So first, just as a kind of reminder and introduction, I want to talk about path integrals. Actually, can we turn off that light there? It's a little bit. Path integrals, which in imaginary time, which lead us to what's called wordline quantum Monte Carlo. And then I want to move on to what we call stochastic series expansion, which in the end is quite similar but a little bit more efficient, often especially when we study spin 1/2 systems, which I will focus on here. And then I will discuss, okay, so these methods work basically at finite temperature. But I also want to talk about a ground state projection method where you explicitly target the ground state. And in the end, it turns out actually to be very similar to these finite temperature methods, so it's quite nice to see that. And okay, so I will discuss the methods, and then I want to show some results for Heisenberg models, and I'm also going to introduce these JQ models that I already mentioned yesterday, and just give some quick results for those as well. Okay, so path integrals, I think all of you know what this is about. So we are interested in quantum statistical mechanics. So in principle, we have to evaluate some expression like that with a partition function like that. And if we are able to get all the eigen values and eigenstates of the system, we can of course evaluate this for any operator Q we like. But the problem is of course that as we discussed yesterday as well, if we want to do this exactly numerically, the basis becomes too large very quickly, and it really becomes impossible to find the eigenstates and energies explicitly. So then we have to do something else. And of course, in the end, we may not be just interested in finite temperature. We may want to go to the ground state, so we can take the t goes to 0 limit. So in the case of classical systems, the ground state is often trivial. Well, that's what I wrote here, and it's true. But of course, in this school, you have been learning about classical systems where that's definitely not the case. So this is, not. But okay, it's still true that it's often the case, but maybe not for the purpose of this school. In any case, even if we work at finite temperature, we can take the limit t goes to 0 and look at the ground state. Okay. So how do we do this if we cannot diagonalize the Hamiltonian? Well, if we want to do some kind of Monte Carlo sampling, then what we want to do is to convert this quantum mechanical thermal average into something where we have some configuration space. So we have some number of configurations. And those, whatever those are, depends on how we do this kind of mapping. But there are some configurations, and each configuration is associated with a weight. And when we consider some operator A, that becomes some kind of function that we often call the estimator of that expectation value. Okay, so if we manage to do that and these weights are all positive definite, then it's great because then we can do Monte Carlo sampling. Of course, it's not always the case that it's positive definite, and if it's not, we have this infamous sign problem. So normally we are restricted to cases where we don't have a sign problem, or we can only do much less if we have a sign problem. But there's still a lot of interesting cases where we don't have a sign problem, so it's definitely worth looking at this kind of approach. Okay, so as I mentioned, there are many different ways in principle to do this kind of mapping and map to some sort of configuration space. So, here I just list 3 of them. So there are these wordline methods that work well for spins and bosons, and the stochastic series expansion also works for the same class of models. And then when we go to fermions, a popular way is to integrate out the fermions by introducing some auxiliary fields and so on, and that leads us to fermion determinant methods. So I will only discuss these two here. And there are other methods as well that I don't want to discuss today. Okay, so this was about finite temperature, but what we can also do if we are interested in the ground state is that we can do something which connects to what I discussed yesterday about the Lanczos methods. I talked about this Krylov space and the fact that we can project out the ground state. So we can take some basically arbitrary state and act with the high power of the Hamiltonian, and when that power becomes large, then up to a normalization, which is not important, we get the ground state. Okay, we could also project with an exponential, and then we get the ground state when beta goes to infinity. Okay, and in the end, as I mentioned, these kinds of approaches, when you actually implement something in a program, they are not too different, actually. Yeah.
Is there any to identify in what particular way, I mean, what particular method actually I should use?
Yeah, so I mean, there are so many different problems you can consider, so it's hard to say something in general, but maybe I will say a few words about that later. But definitely it's true that if I understood your question correctly, if you look at fermions in 2 dimensions, then these, for example, these two methods don't work, and you basically have to use that method. But if you look at spins or bosons, then you cannot use that method, so then you have to pick one of these or some related methods. Okay, so today I'm only going to discuss spin 1/2 models, and of course spin 1/2 is often the most interesting case because it's the most quantum mechanical, but of course other small spin values like spin equals 1 can also be interesting, but let's talk about spin 1/2 models. Then it turns out that if you can write your Hamiltonian using these kinds of operators, which you recognize as singlet projectors, then one can make particularly efficient methods. So in addition to these interactions here, which are, this is really the Heisenberg model, right? The antiferromagnet, if J is positive, the S dot S is positive here. But one can also include some other terms, which are basically products of singlet projectors, and I'm going to talk about those later. Okay, so if we have these kinds of interactions on bipartite lattices, then we don't have sign problems. And I will show you why a bit later. So let's talk about path integrals. So again, what we would like to evaluate is a trace like that. And here the major obstacle is that we have an exponential here, and that's hard to deal with. So one way, which is what leads you to path integral, is to slice up this exponential operator. So, this is basically a time evolution operator in imaginary time. So we often call this, time slicing. So we write this as a series of evolutions for short imaginary times, like that. So, this is completely exact. We haven't made any approximation here. But the point of doing that is that, if this delta tau is small, then we can do some approximations here, some systematic approximations. So what we do first, we insert complete sets of states between all these exponentials. So then in principle, if we can evaluate these matrix elements, then the partition function has been written using some configurations, and those configurations are all those basis states that we sample over. Okay, so but we in general have to make some approximations in order to evaluate these matrix elements. And the simplest way to think about this is really to do just the first order, power expansion of these exponentials, which of course is very good if this delta tau is small. The point is that we can actually take the limit of that going to 0 already before starting to do any simulation. So it's definitely fine to discuss even this very brutal approximation here, which leads to, in principle, to an error proportional to delta tau, because okay, in each of them the error is delta tau squared, but we have many of them, so if you add all errors up, it's delta tau. Okay, so let me be explicit and discuss maybe the simplest case. If we look at hardcore bosons on some lattice. So hardcore means that the occupation number can be only 0 or 1. And a bit similar to the Jordan-Wigner transformation that we heard about before, this maps very directly onto a spin 1/2 XY model. So the XY interaction for spin 1/2 can be written in terms of these ladder operators, and then you see that these act like creation and destruction operators if you just make this mapping of the spins to occupation numbers. So when we do this kind of word line representation of the partition function, each term that we get here, if our basis states are just these occupation numbers, they can be represented as pictures like this. So here you should read the vertical direction as the time direction. So time advances from here, and then we have a periodic boundary conditions in time because we have the same state here and here because we have taken the trace. So in this case we have a system of, I don't know, 12 or 14 sites, and we have 3 bosons there, or you can think of it as 3 up spins in a background of down spins. And then, you know, as we let some terms of the Hamiltonian act on these basis states, things may change. So in the way I have done it here, only, you know, one boson can move at each time slice, because the Hamiltonian is a sum of those, and to connect, you know, 2 states, only one boson can be moved between those states. So you see there are these places where I draw a diagonal, so that's when the boson has hopped. So these differ by just 1, and that means that we have a matrix element here, which is basically delta tau times 1 in this case, because there's no number in front of here. Okay, so then you can see that the weight of the whole configuration, meaning the product of all these matrix elements, is just delta to the nk, where nk is the number of jumps that we have in these pictures. So if there's no jump at all, as you see in a few places here, then it's the one part of this expansion that is active, and the states are the same, and then the matrix element is just 1, right? So the partition function now is the sum over all these so-called world lines. And then I want to point out immediately that there's an interesting thing here related to the fact that we have identical particles. So if we have periodic boundary conditions, then what can happen in the course of this propagation is that these word lines can wind around the system, right? So we have to have the same configuration here and here, but that can be true, as is the case here, also if the particles do cyclic permutations or windings in the course of this propagation. So this could not happen. This would not be a valid configuration if these bosons had different colors, for example. Then, you know, this state would not be the same as that state. But because they are identical, this is also a contributing configuration. Okay, so when we do some kind of Monte Carlo sampling of these configurations, if we only do some small local changes, as I show some examples of here, we can never go from this winding sector to that winding sector because that requires a global change of the word lines. So if we have a good algorithm, we would actually like to sample all these sectors, and you have to be mindful of that. Okay, and I should say again that if you have questions, just interrupt me at any time. Yep.
Is this algorithm an efficient one?
No, so that's a good point. So this is just for the purpose of illustrations. Everything that I'm discussing here, for path integrals is just really to remind you what path integrals is and what we could do in principle. In practice, we would do more efficient updates, and I will mention those as well. Yeah, so these are not just imperfect because you cannot go between these sectors, but the evolution of these word lines as a function of the calculation time would be very slow in general. But this is actually what people used, well, almost what people used to use before we had these more efficient updates called loop updates that I will mention. Okay, so that was just the configuration space that contributes to the partition function. But if we look at some expectation value, then we also have our operator in one of these slices here. So then we also have to see how we can, convert that whole thing into this form with this estimator up here. Okay, so that's very easy if we are considering diagonal operators in our basis, because then this operator only corresponds to extracting some number that depends on that state. Or since everything is cyclic, because we have taken the trace, we could put the operator here or here, it doesn't really matter. So we could in principle average our expectation value also over all the slices, as I indicate here. Okay? We may not want to sum over all the slices because that takes a long time, so we could just do some partial summation, partial averaging. Okay, so that's if the operator is diagonal. If it's off diagonal, it's a bit more complicated. Actually, it can be quite a lot more complicated depending on what operator we have. Because then what happens is that if you have an off diagonal, let me go back to this picture here. If we have an off diagonal operator, then these word lines can, for example, break. If you, for example, have a destruction operator here somewhere, you destroy some bosons and maybe you create a boson somewhere else. So then you go outside this space of configurations that contributes to the partition function, and you have to figure out how to deal with that. So I will just give one example, the simplest example of how to do that. So let's consider the kinetic energy, and again I'm working with this hardcore boson model in this case. So let's take this expression here, and then I just multiply and divide by the corresponding thing that I have in the weight, meaning when I don't have any A there. So, yes?
Is there an exponential
Sorry, I didn't get that.
Is there a Hamiltonian missing in exponential minus
Let's see. Oh, yeah, good. Yeah, exactly. Yeah, that's. Nobody has pointed that out before. This audience is unusually attentive. You find typos that nobody noticed before, although I've given this shown this slide in many occasions before. Yeah, of course, there's an H missing there. Thanks. Yeah, so here, this is multiplying and then dividing by the same thing, and now I have this, a single kinetic energy operator acting between two sites up there. So then what you can see is that, okay, now we can just write this as our weight function. It's exactly our weight function that we discussed before. And then what we are left with here, you see that you have a lot of cancellation. So everything cancels out here except, you know, two of these guys here, the one where you have k and one of the rightmost one in the denominator. So then you get something which is actually quite simple. And the point is that the kinetic energy operator just, you know, does the same thing as it does in the partition function. So it doesn't take us actually outside the space of continuous word lines, even though it's an off-diagonal operator. So if you work it out, you can see that if, okay, so we can also make this approximation in this particular case because eventually delta tau is going to 0, so I just, you know, replace that thing here by just kij, and then you can see what you get. So if you evaluate this at somewhere where you have a jump, you get 1 over delta, and if you evaluate it, for example, in this slice where there's no jump, you get 0, right? So then you can also average that over the whole space, and you can do averaging in time and in space. So in the end, what you have to do is you just have to count how many of those jumps do you have in the world line configuration. So if I call that, you know, Nij, meaning how many jumps on the bond ij, then the kinetic energy on that bond is just that number divided by beta. And why divided by beta? Well, because we had 1 over delta tau there, and then we did an averaging, and delta tau is related to beta by the number of these slices that we average over. So then if we do the total kinetic energy, indeed, as I said already, and if I put back the sign that I had removed at some point, the whole kinetic energy has a minus sign in front of it. We just count the jumps and divide by beta. So then we can see something useful, namely if we just look at you know, the fact that the kinetic energy has to be extensive, that should scale as n, and that means that the number of these jumps must scale as beta times n. And why is that useful? Well, it tells us that if we make delta tau smaller and smaller, at some point the number of jumps will no longer increase. So you will get a lot of slices where nothing happens, and you will just have a number of events proportional to beta times n where you have these jumps. And that's actually why in the end one can take the continuum limit, because you actually don't have to store all these configurations completely. You can actually just store the locations of these jump events, right? Which helps a lot when delta tau becomes small, because the configurations in their full glory become too big to store. Right, so we can actually, because of that, take the continuum limit. Let me say something more about that in a moment, but so for now I didn't discuss how to deal with interactions. We had only a kinetic energy, we didn't have any potential energy. So if we also have potential energy, then we can do this split operator or Trotter approximation, where we split up the exponential in two factors. And then since the potential part is diagonal in my basis, it just becomes a number that goes outside the matrix element. And then again, we have to do this for all slices. So then the weight that before was just delta to the nk also get this exponential factor where we have to look at the potential energy at all these slices. So then if we actually do Monte Carlo updates, if you ask about what the acceptance probability should be and so on, if we make a modification, we have to look at the change in that number. So this would be the Metropolis algorithm, the simplest case. But again, not very efficient. So if I take the continuum limit, then I can redraw the configurations in this way. And now you see that what I would store here is just the times at which these jumps happen, and of course, where they happen. Okay, so in principle, one could do some local updates here. Let me not go through the details because nobody is actually doing this. The point is here that one has to be careful to satisfy detailed balance when you do the sampling. So you have to consider when you, for example, introduce a kink, you have to consider what's the volume of the space in which you actually do it. You have to consider that when you want to satisfy detailed balance. But as I said, nobody does this because there are actually much more efficient ways called loop and worm updates introduced by these people here, which allow us to make very big changes in a very efficient way in these configurations. So one would not normally do those local updates. Okay, so let me not discuss details about that because a bit later I will show you some method where that can be done even in an even simpler way, namely in this stochastic series approach. But before I go there, maybe I should see again if there are any questions about the path integrals, because I'm not going to say more about that. Yes, please. Maybe you can use the microphone, it's a bit hard to hear.
My question is that you said that if the lattice is bipartite, then we can have no sign problem.
Right.
But suppose the lattice is bipartite, but the terms in the Hamiltonian are giving rise to frustration.
Yeah, okay, yeah, that's a good point. So that definitely can happen. So I haven't really discussed the sign problem in more detail yet, but you're absolutely right. It's not just the geometry of the lattice, it's what interactions you put there. So I will come to the sign problem soon, and I will make some further comments on your question then. Yes, please.
What happens if t equal to 0, or if we take the limit there is divergence?
Oh, okay, good point. So in the end, there is no divergence actually because, let's see. Yeah, so this relates to this thing here. So it looks like here if you make some change, for example, you remove two operators, that the probability of doing that should be 1 over delta squared, right? Which seems crazy, but actually when you consider all the possible ways of making these changes, meaning that this kink that you insert here can exist anywhere and be arbitrarily big within these limits, then you actually get a well-defined number that doesn't depend on delta. So let me not go more into that because it's a bit complicated, but in fact, when we look at these loop algorithms too, you can work out all the acceptance probabilities and so on for finite delta, and then you will see that when delta is small, nothing actually depends on delta anymore. So it does work out even if it looks like you have some divergence. But okay, maybe your point is more theoretical. So if you try to do something in the continuum, let's say you have particles in continuous space, then you could actually not also make the time space continuous. Then you get some serious divergences that nobody knows how to deal with. So maybe that's what you refer to. So if you can either have continuous time and discrete space, or you can have a continuous space and discrete time, but not both continuous. So it's related to the boundedness of the spectrum of the Hamiltonian and things like that. So on the lattice, you can make the continuous time. Okay, so one more question, yeah.
How do we generate these states?
You mean generate these configurations?
Yes.
Yeah, so that's what I don't really want to talk about in the context of path integrals, because I want to move to this method here where that's much easier. So let's just do it there, if that's okay. Okay. So this stochastic series expansion is basically an alternative to the traditional path integral. So instead of doing this slicing trick that I explained, we do something that at first sight may seem a bit crazy, namely you do a Taylor expansion of e to the minus beta h. And of course, you know, that has terms going up to infinity, and that may bother you, but you will see that it's actually okay. So this was actually proposed by Hanscom, who was a famous statistical mechanician in the 1960s. but nobody really used it. People tried, but it only worked for a small number of models in the way he had proposed it. But it turns out that one can generalize it and actually modify it a bit to make it work for a broader range of models. So that's what I want to talk about. But basically we do the same, well, we can consider it as in a similar way as when we did the path integral, namely insert complete sets of states between these Hamiltonians, okay? So instead of the exponentials that we had before, now we just have these individual Hamiltonians, and before we could do the expansion of e to the minus delta tau h on the slices, but now we just have h itself. Instead, there are some weight factors outside. Okay, and again we have the sum up to infinity, but you will see that that's no problem. So if we go to the case of these hardcore bosons that we just considered, these matrix elements are very simple. Again, the states can differ only by single jumps. So you can draw pictures exactly like those that I showed you before. It's just that the weight associated with those pictures is a bit different. So in the case of the hardcore bosons, instead of delta to the number of jumps, this is just beta to the n over n factorial, where again n is the power in the expansion. Okay. So let's again look at what happens if we want to evaluate the energy expectation value. So then what we do is, this was the partition function, right? So if I look at the numerator of the expression, we have one more h there, because now h is our operator. So here you see that I have a sum over n plus 1 inserted complete sets of states, well, including the one for taking the trace. So one of them, for example, this one corresponds to the operator that we are actually measuring. So if we are not looking at the energy, it would be whatever operator we are interested in. Okay, so now we have to get some estimator for h out of this. And a very easy thing that one can do here is you can just relabel this summation index. You see that in the partition function and in this thing, we have really the same kind of sum. It's just that here we have one more slice or one more h. But we sum over all of them, so if I just relabel n plus 1 to n here, then I get an n over beta outside, in addition to that factor, just to compensate for the fact that the index, summation index changed. But now this looks exactly like the sum we have in the partition function. Only this thing is different here. And that means that this is actually our estimator for the energy. Okay? So then we can immediately see that the energy is the expectation value of this expansion power divided by beta. Okay? I hope that's clear. So this was, again, first derived by Mr. Hanscomb a long time ago. And what he also derived, and it's very easy to do, if we just take the temperature derivative of E, you get the specific heat, and that looks like a fluctuation of N, except there's also a minus expectation value of N there. Okay? So now if you think what happens when we go to 0 temperature, normally the specific heat should go to 0 in that limit. So then you can see that that tells us that if C is 0, that N itself equals the variance of N. So what we can read out of that, plus knowing that the energy itself has to be extensive, we can see that, okay, this thing has to be extensive, proportional to N. So N, the number of operators, or let's say the expectation value of the number of operators in this sum is proportional to N times beta, and the width of the distribution is the square root of that. So of course that means that the relative width of the distribution becomes very narrow, and that means that actually this sum up to infinity is actually exponentially cut off at some n proportional to n times beta. So actually maybe I can have some light, then I can show something related to this. Thank you. So if we consider this number here, e to the x. Okay, let's Taylor expand e to the x. So we just get sum over n, x to the n factorial, right? Okay, now let's call that omega n. Let's just call that the weight for given n, sorry, w of n, I should say. Okay, now we can draw this function here. And okay, it's a very simple thing. It's a number like that. So you can easily compute from this that actually it's the Poisson distribution, right? So the expectation value of n, if you compute it like up there, is just x. So, and again, the distribution will be very narrow, approaching some Gaussian-like thing when n becomes large. So this is almost identical to what we have here, except this weight involves a lot of matrix elements and so on, but in terms of the length of the expansion, it looks a bit similar. If you think of beta times h roughly as beta times the energy, right? Then you get something like that. Yeah.
So basically we are expanding in exponential, right?
Yeah.
And does it imply that at large temperature you can very well work with very few terms?
That's right. That's right.
Like low temperature you have to include a lot.
Yeah, exactly. And the nice thing, as you will see a bit later, is that you don't have to know how high you have to go. The program can itself very easily detect if, well, it will sample over, those things itself. So, okay, as I will discuss on the next slide, we can actually put a cutoff here, but the program can itself decide what the cutoff should be. Oh, okay, yeah, good point. So, yeah, in general, it would cause a serious problem, but as I will explain in a moment, in many cases, in fact, those cases where this would be useful, that sign will exactly be cancelled by signs appearing here. Okay, so that's exactly, the cases where this will be useful. We will come back to that in a moment. Okay, so related to this kind of expansion here, you see if I have something that really decays exponentially, if I put a cutoff here at some point that I call L or M, I forget what I call it, that will not cause any approximation of importance if this is far enough to the right. So it makes things a little bit easier if you actually put a cutoff, but again, the cutoff can be adjusted automatically. So the reason why that is better is that then our configuration space has a fixed size. It's not, fluctuating, shrinking, and expanding. So if I have a term which has 10 operators in it, and let's say I have decided, or the computer has decided, that the cutoff will be at 14, then I just insert 4 unit operators in this sequence. So here, by the way, this index here just corresponds to terms in the Hamiltonian. So H is a sum of some number of operators, and I give those individual operators that act on a bond, for example. I give an index to those, and those are sampled as well. So we don't evaluate these matrix elements for the full Hamiltonian. We just sample over the contributions to the Hamiltonian as well. Well, okay, that's what we do, but if you put the complete set of states, that's also somehow equivalent. Anyway, we insert some unit operators there, and then we say, okay, we can do that in many different ways, right? So there's some overcounting if I just do that. But we know exactly how many ways we can do the insertion, so that means that we can exactly compensate for this overcounting by dividing by that number. So then this minus beta n over n factorial instead looks like that. So you just modified that weight function a little bit. So this is what we normally do, although you can actually also work in the space of fluctuating sequences. That's also okay, but this is a bit more efficient. Okay, so let me be a bit more specific and discuss a particular case, namely the Heisenberg model. And now let's do it in 2 dimensions. So this is our Hamiltonian, and I consider a square lattice here for illustration. So the nice thing here is that you can write the Hamiltonian in a way which is not really dependent on the lattice. You just need to come up with some scheme of labeling the sites and the bonds. So if you write the Hamiltonian like that, then you can actually use the same program for many different lattices. You just have to make this kind of list. So here I have labeled the sites in a certain way, and I have labeled the bonds in some natural way. So B here refers to the bonds, and IB, JB, those are the sites connected by a given bond. So for example, bond 22 connects sites 6 and 10, right? So I is 6 and J is 10, okay? And NB is the total number of bonds, which in this case is 2 times the number of sites. Okay, now let's also split up this interaction in its diagonal and off-diagonal parts. So we consider the standard basis of the up and down spins, and we write the Hamiltonian as those parts, diagonal and off-diagonal parts. But I'm going to add a constant to the diagonal part, and you will see why in a moment. So here it looks like I have the wrong sign, but I will correct for that by doing minus j there. And this is the off-diagonal part. So I corrected for that sign by putting minus j, but then I get a minus sign in front of the off-diagonal part. And that's, in the end, what's going to cause the sign problem, if there's a sign problem, because this minus sign here will be cancelled by minus beta times h, right? There's a minus beta there. But this sign could potentially cause some problems. Okay, so for now, let's look at the matrix elements of these bond operators. So the reason we added a quarter here was that if we do that, then all the non-vanishing matrix elements are 1/2. So they are the same for the diagonal and off-diagonal terms. So you see the up, down, that's a diagonal one. So by the way, I call the diagonal ones H1 and off-diagonals H2. So they are all off-diagonal, diagonal, they are all 1/2. Okay. So these are the only 4 we have, by the way. If you have up, up, for example, you know, that is destroyed by both these operators. Okay, so now I write the partition function in a slightly different way. That explicitly refers to the fact that I have 2 indices on my Hamiltonian operators here, and I have gotten rid of those complete sets of states that I inserted, because when we deal with the SSE method, it's easier to just think of it as a sequence of operators that act on one state. You don't necessarily need, at least at this level, you don't need to put in any intermediate states there. So we have some state, and we sum over those states because we have taken the trace. We have a product or string of these diagonal and off-diagonal operators, and we have to sum over all possible such strings. So that's what this Sn means. So Sn is an index string, I should say string of index pairs in this case, that refers to these Hamiltonian operators. Okay, and we still have to sum over n, but again we can also do the truncation that I talked about, so we will do that. So if we do the truncation, this is the form, and I mentioned that, okay, we have inserted unit operators. The unit operator doesn't do anything, but they are still needed there, but I give them now a different name. I call them H00, just to conform to this notion of used for the other operators. Okay, and this is again the weight function, and now you see in this case, because all those matrix elements were 1/2 for the non-zero ones, the weight function doesn't even depend on these operators, as long as that sequence of operators propagates this state back to an identical state, so that this whole matrix element doesn't vanish. If that's true, then the weight function just depends on the number n. Oh, and by the way, here I have changed notation, unfortunately. L is what I called m before, it's the truncation of the expansion. Okay, so we may still want to look at those intermediate states that I don't include here in the notation. But if I just propagate my state with part of the string, I call that alpha p, right? So then I can make a picture here of some typical configuration. Yep.
Here is it important to state that you're choosing these h, a, comma, b such that if you hit this thing on a hit, then it doesn't produce some superposition of.
Oh, yeah, that's an important point. So yeah, let me jump back to here. It's pretty clear here, but in some other case, you have to be careful. So here, if you act with one of these operators on a state, as Arnab said, you generate another basis state, right? It doesn't split up into a superposition of two states. So for example, if you had a spin 1 system, then these ladder operators, for example, if you had act on 0, 0, you get up, down, but you can also get down, up. So then that creates a superposition. So then I would split this up further into its two terms, right? That term and that term. So I would have 3 different operators. Then all those would by themselves not cause this kind of branching. For spin 1/2, it's okay to write it like that because only one of them can actually do anything. But if you have an up and a down spin, one of the terms will, flip both of them. The other term will just destroy the state. So only one of these will be doing anything if we consider this product here. Okay, so it always helps to look at the picture, so let's do that. So this is for a spin chain of 8 spins, and here red and white or black circles correspond to up and down spins. So this state down here corresponds to the alpha, and then I have a bunch of operators, and they are now indicated by these bars here, in case the operators are, the actual Hamiltonian operators. And then I also draw all these propagated states, which you can again think of as, the complete set of states that I have inserted. And for a given string of operators, those states that contribute would be unique, the ones shown here. So what we have here is that the first operator that acts is this one here. So it's a diagonal operator, so it doesn't really do anything, it just sits there. Okay, the next one is an off-diagonal operator, so it actually flips the spins, as you can see. Then on the next slice, I have a unit operator, so I don't show anything here, nothing happens. Then there's again an off-diagonal, and so on. And you can see the last state is the same as the first state, as it has to be because we have taken the trace, or we are taking the trace. Okay, so this index P, which in some sense is related to imaginary time. So if we do path integrals or word line methods, we call this the imaginary time direction. In this case, it's just a discrete index, but it can be very easily related to imaginary time, but I will not discuss that explicitly. Basically, if you take a fixed imaginary time that corresponds to a distribution of locations in this sequence. Okay, what else? Well, so we have to store something in the computer, and this now corresponds to what I mentioned before about the continuous time case, where we only want to store the events. So here, these operators are our events. So we store, for each of these slices, if you will, we store these A and B indices. So A just tells us, is it a diagonal, off diagonal, or unit operator? And the second index refers to the location on the chain. So 7, this is the 7th bond. The next one is at bond 4, and so on. What we actually can do in practice is to pack this into a single index according to a simple formula. So here, it's basically, if it's diagonal, it's just twice the bond index. If it's off diagonal, it's twice the bond index plus 1. So even and odd would be diagonal and off diagonal. So that's what we actually store in the computer. Okay, now let me come back to the sign problem again. So here we still have this annoying sign that probably could kill this whole thing. But as you see here, what we have to do in order to satisfy all the constraints is that the sequence of operators has to propagate this state back to itself. And then I think you can convince yourselves that if the lattice is bipartite, I need an even number of these off diagonals, as you see here, because each spin that is flipped has to be flipped back, and each time 2 of them are flipped, and then the bipartiteness really makes it necessary to have an even number of them. Okay, but if the lattice is not bipartite, then you can also easily see that an odd number of diagonals is okay, as I illustrate here. So here we start with 3 spins on a triangle. So that corresponds to this thing here, which I had on a linear chain. Now I just take a triangle. And then I put an operator on these 2 spins here. Okay, what that does is it flips those spins. Then I can flip those 2, gives me this picture. I can flip those 2, that gives me this picture. So now I'm back to the original configuration, and I did that with 3 spin flips, right? So now N2, which is the number of off-diagonal operators, is odd. So this term actually comes with a minus sign. So this you can do anytime you can draw a loop with an odd number of bonds, closed loop with an odd number of bonds on your lattice. So that's basically another way to define a bipartite versus a frustrated lattice. So if you have actually a chain, and you have periodic boundaries, but the number of sides is odd, that's also strictly speaking a frustrated lattice, because then if you go around the whole chain, you have a loop with an odd number of bonds. So we would also be restricted to an even number of sides if we have periodic boundaries. Okay, and any more questions about the sign? Yeah.
Okay, I forgot, why are we acting only one bond at a time? Is it possible to do it like that?
Yeah, so that's because, we sum over these individual terms in the Hamiltonian. So given configuration is really a string of these bond operators, right? So each time something happens, it's only happening on one bond. Yep. Right. So what we actually store then in the computer is basically, okay, I gave some sort of data structure up here. We have to store only one of these spin states. We don't have to store this whole thing. we store one of the spin states, and we store, this index sequence. So it's a pretty compact storage of the configuration. So one point that I would like to make here is that we effectively work here in continuous imaginary time, like in the case I showed you before, where we really did imaginary time and we took the continuum limit. But this is a discrete representation of continuous time. And that's in the end what makes this more efficient, because you don't have to deal with real numbers, you deal with integers only. Except when even I guess when it comes to generating random numbers, that's also typically done with integers. Okay, so this is one way to visualize the configuration and how it's stored. When it comes to doing those loop updates that I already mentioned, we actually also want a different kind of storage and representation of our configuration. And for that, I want to introduce the notion of vertices. So we have these bond operators, and they are diagonal and off-diagonal. So when we act on two spins, if the operator is diagonal, nothing happens, right? So this is the kind of, this is what I call the vertex, the spins that go in, so to speak, and come out of the operation. So these are the two diagonal vertices, and these are the two off-diagonal vertices. And these are, in this particular case, the only allowed ones. If you have other models, you would have potentially other vertices as well. So if I go back for a moment to this configuration here, so as I mentioned, we don't need to store all these spins here. And one reason is that in most cases, nothing really happens with these spins. So for example, if I look here, there's an operation, and then nothing happens on those spins until at some later point there's another operation. But these are just constants, so we can just think of this as, okay, there is a spin here, and it's somehow connected to that spin here, meaning that everything between is unchanged. And that's what we do in this linked vertex storage paradigm, that we draw the kind of picture that we did before, but we replace all same spins by just straight lines like that. And in the program, we think of this as a linked list. So we have a list of these vertices, and these vertical lines here tell us how they are connected to each other. And I will need that because when I will make these so-called loop updates, I'm actually going to move around in this list in a certain way. So the way this is stored in the computer, it gets a bit technical, so I think I don't want to say anything about it. Here is just an example of such a list. So that, these vertices have what we call 4 legs. These numbers here are basically telling us how, for example, this leg number 2 of this vertex is linked to leg number 1 of that vertex. So if we, for example, go to that one, it's number 3, right? 1, 2, okay, so it's, where are we? Sorry. Okay, so it should be this one. There's some cases where there are these unit operators too, but this is, corresponds to that one. So this leg here is leg number 2, so we have to look at leg number 2. It should be this one. So there's the number 18 here. Actually, it's this one. So this is the 18th position in the list, contains the number 44. So that tells us that this is linked to 44, which is up here, which apparently is not what I wanted. It's a bit hard to see in this list. Anyway, let me not try to explain it because I will twist my neck too much if I could look here, I guess. But anyway, so this list allows us to jump around in this linked vertex list according to exactly these bonds or vertical lines here. Okay, right. So let me talk about the Monte Carlo sampling scheme. So there are actually two kinds of Monte Carlo updates that we do here. So I sort of assume that everybody is familiar with basic Monte Carlo, for example, of the Ising model, that you have done something like that. So you know, when you simulate the Ising model, you pick a spin, then you attempt to flip it, meaning you are not yet sure if you are actually going to flip it, because you have to calculate how much the energy changes when you actually flip it, and then there's for example, the Metropolis algorithm tells you what is the actual probability for flipping it. So when we do these quantum Monte Carlo simulations, the configuration space is more complicated, and we have to do some updates, some changes in the configurations, such that we can, when we start from an arbitrary configuration, we can reach, in principle, any other configuration. So we have to be ergodic. So in this case, it turns out we have to use two different kinds of updates. So the first kind of update is basically to change the number of operators. So in this case, I have 8 operators, and I have some of these unit operators where it's just empty. So those are not counted. We just count n as being the actual number of these bond operators. So I need some way to insert and remove operators. So in general, what we do before getting to details is that we have some configuration, we change it to some other configuration, and given the weight function, we have an acceptance probability, and this is just the Metropolis acceptance probability that tells us that we have to evaluate the weight ratio, and that's basically the acceptance probability. But in this case, I have something else here as well. So in general, when you go from one configuration to another, there is some probability before you consider the Metropolis step, just saying, okay, I have some number of choices to go from left to right, and then I pick one of those. So there was some probability of making that particular attempt. And to satisfy detailed balance, you have to make sure that if there's a different number of way of going in the left direction, that you compensate for that. So this you don't really encounter if you look at the Ising model, because when you flip a spin, okay, let's say you pick among your spins, you have n spins, so the probability of picking a particular spin is 1 over n, and then you can flip that one. If you go in the opposite way, there's also a probability 1 over n to flip that, or to pick that spin, and then you can flip it with the Metropolis probability. So the number of choices when you go to the left and the right is the same. But if it's not the same, you actually have to compensate by also multiplying by the ratio of the number of ways to select, or let's say the select probabilities. So this will become very clear when I show you this example here. So what we call the diagonal update. So this is exactly the update that we need to increase or decrease the number of operators by 1. So let's say I have a case, for example, here there's no operator. So it's empty here. Then I can insert a diagonal operator here, because that doesn't violate any constraint, globally, so to speak, as long as I put it between two opposite spins. Then I have a new allowed configuration. Okay, but then I have some choices where to put it, right? In principle, I can put it on n different bonds. Some of them are forbidden, so if I happen to select that, I would just cancel the update and do something else. But then the point is when I have some choices when I go to the right. But when I go to the left, I don't have any choice. The only thing I can do, at least the way we do it here, is to remove it. There's only one way to remove it, right? So then there's actually an imbalance if you don't correct for that. So you have to consider, okay, how many choices do I have to insert it? How many choices do I have to remove it? So when you work that out with the weight ratio and the selection probabilities, this select probability to insert an operator is just one of the number of bonds, although some of those may be illegal, so that means that if you have selected that, you will actually not do it because the probability of actually doing it would be 0. But still at the select stage, you consider that. But when you remove, there's only one way to do that, so the select probability is 1. So then if you just use that formula, you get these, you combine these and you get these pretty simple looking formulas for the accept probabilities. Right, so is that clear how that is done? Right. Okay, so that increases or decreases the number of operators, but it only involved diagonal operators. So we also need to do something with off-diagonal operators. By the way, how much time do I have? 17 minutes, okay, so it's, I should be okay. So off-diagonal operators. Okay, so what can we do to change the number of these off-diagonal operators? Well, one simple thing that we could do, and that corresponds to this simple update that I showed you in the case of the path integral. I could look at a pair of off-diagonal operators where there's nothing in between and just change those to diagonal operators. Then I have a new valid configuration. Okay, and since I have periodic time boundary conditions, you could, consider doing it, like that, or changing the spins that are between in the other sense, so to speak. But in this case, only this would be allowed. So, for example, in this case, which I showed with these dashed boxes, I cannot do that because there's something in between there. But if I consider the periodic time boundaries, I could actually still do it because I can change the spins there, and then that would change as well. So that can be done, but it's not very efficient. And that's where these loop updates come in, and that's where I really need this linked vertex storage. So it's actually very simple. So you work in this representation and you just pick a starting point. For example, I pick this as my starting point. And then you start to move, and you move in this list that you have constructed, so you sort of jump to that spin there. And every time you touch a spin, you will actually flip the spin, and you will actually also, let's see what happens. You change the spin, then you move to the second spin on the same operator, and then actually the operator itself will change as well, from diagonal to off diagonal, or vice versa. And then you just continue along those, using those links. And eventually you will get back to where you started from, and then you have a closed loop. And this is completely deterministic. You just have to find the loops. And it's again very easy with this construction that we have. And this is very efficient because it changes, potentially you can change a lot of operators. You don't change the number or location of these operators, but you change the type of operators, and in the process you may also change the spins that you have stored. So the first update is just to change the number and also location of operators, and the second update is just to change the types. So this is all what we actually have to do to simulate this. So now let me just show that this is actually working. So, okay, we should also, before I do that, talk more about how we adjust this cutoff that I called L, or at some point I call it M. So what you simply do is you just keep track of how many operators you have there, and if it's getting too close to the cutoff, you just increase the cutoff. So here is, and you can use some simple formula for that. It's not so important how you do it. So this is showing as a function of the number of Monte Carlo sweeps I do for some particular system. It shows the cutoff, it shows the actual number of operators and the maximum number reached so far. And you can see that the maximum number reached so far here is still far below the maximum. So that means that I have not made any approximation. If you actually collect a histogram of the number of operators, it looks again like a Gaussian, and it becomes very small when you get the cutoff, which is more than 6,000 up here. So the cutoff has been no approximation at all here. So that's very easy to do. Okay, let me show you some comparison with exact diagonalization results that tell us if this is working or not. So here's an example for a 4x4 Heisenberg model. I calculated the magnetic susceptibility, and I can compare it with exact diagonalization. So the solid curve is the exact diagonalization for that lattice size, and these red dots are the Monte Carlo results, and you see that on that scale you cannot see any difference, but if you look at it, if you look at the difference between them, and actually I did this calculation in two different ways, let's not worry about what they are, but for example, if you look at these red arrow bars, you see that the deviations seem completely consistent with the arrow bars, and the deviations are of the order of 10 to the minus 6 or less. So these were really long simulations just to test that there's really no systematic errors here at all. Then you may ask, well, okay, maybe it works for the small system, but does it work for the big systems? If you go to a bigger system, in general, that would be hard to rigorously prove mathematically, but for at least in one dimension, we have the beta ansatz that is exact. One can do it for finite system size, and one can compare with that. And here I just illustrate that we can also really get ground state results by going to very high beta, low temperatures. So here this is a logarithmic scale of beta. Beta is 2 to the power m, and I show some results for 1024 and 4096 sites, and it's compared with the ground state energy from the beta ansatz. And you see that it agrees very well, again to some pretty insane precision. This was not that long a simulation even. It took maybe a couple of days, maybe even less. Okay, so I think I have a few minutes to talk about valence bonds. I think what I will do, I will probably not finish this today, so maybe tomorrow I will spend a few minutes completing this lecture. But anyway, let's talk about ground state projection using valence bonds. So this is a very convenient basis to use, it turns out. So I think everybody is familiar probably with, okay, we are not talking about valence bonds in chemistry, we are talking about singlets. So if you take a bipartite lattice, you can make singlet coverings such that you only connect A and B sides, and this turns out to be a massively overcomplete basis for the singlet sector. So one can expand any singlet in these kinds of states. It's overcomplete, so in principle there are many ways to do that expansion, but actually if you want to keep these positive, I believe actually it's unique. So for a non-frustrated system, they can be positive, and those positive numbers are probably unique. It's not so important actually for what we're going to do. So this basis is overcomplete, and it has the property that all basis states actually overlap with each other. So if we take two states illustrated here, to calculate the overlap, it turns out that you have to find loops. So you superimpose these, and then some loops are formed, and you have to count the number of loops. So if there are many loops, the overlap is large, and if there are only a few loops, the overlap is small. And it turns out that spin correlations or normalized correlations of the kind we need when we actually measure these things in simulations, it's also very easy to get from this loop structure. You just have to check if the two sides belong to the same loop or different loops. So if they belong to different loops, you get 0, and if they belong to the same loop, you get 3/4 times a factor, which is just plus or minus 1. And one can calculate more complicated correlation functions too, it turns out, and everything is basically related to the loop structure. So one can do ground state simulations in this basis. So as I already mentioned, if you act with a power of the Hamiltonian, you project out the ground state. And if we do that with valence bonds, there are some very simple rules how valence bonds are projected. So this is now an operator string exactly of the kind that we discussed in the SSE method, but in this case, you can think of this as a fixed number of operators. You don't have to actually sample the exponential, although you could, but you can just do h to a fixed power. So then if you look at what happens when one of these Heisenberg operators, which is written in the form of a singlet projector, what happens if you act on valence bonds. So if you act on a valence bond, okay, the valence bond is an eigenstate of this operator, so you just get 1 and nothing happens to the bonds. But if you act between two bonds, as is shown here, these arrows have something to do with signs. Let's not worry about them. But what happens is that if you act here on these black bonds, if you act between them, you actually form a bond between them, and the other two spins are also connected by a bond. So you just reconfigure these bonds. So in that way, you can actually very easily evaluate a whole product of these operations. So one can measure expectation values, but let me show you some pictures before I probably should end today. So you have to project out of something, and that something can be some variational state, or it can just be something more simple-minded. In this case, let's just say that we project out of a short bond configuration, same on the left and the right, because we want to measure some expectation values, so we have to project a bra and a ket. So then we have these Heisenberg singlet projectors that act on these bonds, and they reconfigure the bonds in various ways from the left and the right. And then I have to stick an operator there in the middle. And here again, you will basically form this kind of transition graph as we discussed here. So in the middle there, you will form that loop structure, and then you can evaluate your contribution to the operator A from that configuration. Okay, so I think I should probably stop here, and I can continue a little bit on this tomorrow.